Good day. A partial differential equation is an equation relating the partial derivatives of some unknown function or solution. An example of partial differential equation is heat equation. Today, we are going to solve a one-dimensional heat conduction under partial differential equation. So, from the Taylor series, u of x plus h comma t is equal to u of x comma t plus h times partial derivative of u with respect to x is equals to h squared over 2 factorial times the quantity second partial derivative of u with respect to x. This is the first equation. For the second equation, u of x minus h comma t is equals to u of x comma t minus h times partial derivative of u with respect to x plus h squared over 2 factorial times the quantity second partial derivative of u with respect to x. Here, x is the temperature. If we add the two equations, u of x plus h comma t plus u of x minus h comma t is equals to 2u of x comma t plus h squared times the quantity second partial derivative of u with respect to x. Hence, the second partial derivative of u with respect to x is equal to u of x plus h comma t plus u of x minus h comma t minus 2u of x comma t all over h squared is equals to u sub I plus 1 comma j. From the first equation, we get u of x comma t plus k is equals to u of x comma t plus k times the quantity partial derivative of u with respect to t. So partial derivative of u with respect to x is equals to u of x comma t plus k minus u of x comma t all over k is equals to k sub I comma j plus 1 minus u sub I comma j all over k. Now, we have an example for one-dimensional heat conduction equation, which is a parabolic equation. Second partial derivative of u with respect to x is equals to 1 over x squared times partial derivative of u with respect to t, wherein x is equals to any constant. U sub I plus 1 comma j plus u sub I minus 1 comma j minus 2u sub I comma j all over h squared is equals to 1 over d squared times the quantity u sub I comma j plus 1 minus u sub I comma j all over k, in which h is not equal to k. Let r is equals to alpha squared times k all over h squared. Ru sub I plus 1 comma j plus Ru sub I minus 1 comma j plus u sub I comma j times the quantity 1 minus 2r is equals to u sub I comma j plus 1. U sub I comma j plus 1 is equals to r times the quantity u sub I plus 1 comma j plus u sub I minus 1 comma j plus the quantity 1 minus 2 times u sub I comma j. This line on the right shows the boundary values of the equation. So the problem is to solve the equation second partial derivative of u with respect to x is equals to partial derivative of u with respect to t, given u is equals to 0 and u is equals to 100 for all time t iterations. H is equals to 0.6, k is equals to 0.135, u sub 1 comma 0 is equals to 10 degrees, u sub 2 comma 0 is equals to 20 degrees, and u sub 3 comma 0 is equals to 30 degrees. So our solution is alpha squared times k all over h squared is equals to 1 times 0.135 all over 0.6 squared is equals to 0.135 over 0.36 is equals to 0.375. Our boundary conditions are given by u sub 0, comma 0 is equals to 0, u sub 1, comma 0 is equals to 10 degrees, u sub 2, comma 0 is equals to 20 degrees, u sub 3, comma 0 is equals to 30 degrees, and u sub 4, comma 0 is equals to 50 degrees. The temperatures for the first, second, third, fourth, and fifth iterations are all 50 degrees. What we are going to find out in Jupyter Notebook is the solution of this heat equation. First, we have to input iterate is equals to int, open and close parentheses, 5, because we have 5 iterations. Second, row is equals to int, open and close parentheses, 5, because we have a total of 5 boundary values, 0, 10, 20, 30, and 50 degrees. Here, our code is based on the finite difference method. Alpha is equals to float, open and close parentheses, since the value alpha is 1. H is equal to float, open and close parentheses, 0.6 because the value of H is 0.6. K is equals to float, open and close parentheses, 0.135 because the value of K is 0.135. R is equal to double, open and close parentheses, alpha raised to 2 times K to be divided by H raised to 2, close parentheses. This is the solution that we wrote to solve the equation. Let us run the code. We have to enter the boundary values 0, 10, 20, 30, 50. So the boundary conditions look like this, just like what is shown in the PowerPoint presentation. And this is the solution of the heat equation.